Hi everyone, I'm Bowen, the chief scientist at Nous Research, and today I'm going to present to you guys something very interesting, and I hope you guys like it. So, rethinking the transformer. So let's start. So you must have heard this a lot, right? Like the age of scaling is over, right? This word has been like repeated over and over in the recent years. I mean, recent months, not even years. Is that some claim that there's not enough data, right, for scaling transformers up to like infinity. And my current assumption on this is that it's probably not the case. And today I'm going to talk about why I think so. So there's another way to continue scaling. And to do that, let's just take a step back and look a little bit at the bigger picture, right? So here you have a standard S-curve progression of technological progress that shows like improvement in AI, right? You have the effort on the x-axis, which shows like how much resources and like research compute we put into the problem, and then you have the model capabilities on the y-axis. And you have this like kind of, you have this exponential kind of curve at first, but then it slows down, right? So at first we had language modeling scaling, and then after that we start to have like use cases of like multimodal LLMs, tool use agents, right? And let me give you a few examples. At the beginning, you had like GPT-2, GPT-3, that was at the very early, times, right? Where you only had pre-training. You didn't even have SFT or all of those RL and anything, GRPO. And after that, they scaled up to GPT-4, and everyone's like, wow, this model is very good. It was just pre-trained, right? And then you got to the age of like GPT-03, DeepSeek R1, where we started to like, maybe scaling is not everything. And we started to like look into alternatives like multimodal LLMs, where like you have this example, Gemini, GLM, there's also like Qwen VLM, there's DeepSeek OCR that just came out. And for me, I would put that in the very early like curve, because we just begun to explore like use cases and multimodality, right? Like the multimodal models we have today is only like barely images and like possibly audio. Like we don't have open source audio models. We also, the video models are also very rudimentary. They're not like with the LLM, right? They're like separate image generation models. So yeah, let's talk a little bit about the potential limitations of current multimodality, right? So there's a huge bias towards language. So they kind of treat other modalities as second-class citizens. What I mean by that is like they don't treat them the same as text, right? You have the text decoder, but you have vision adapters, audio adapters, like you have diffusion, image, like weird adapters on the input and output, right? Those are like added on top of the LLM. And most are not generative in the sense where, for example, some models like Qwen VLM, it's only in the input, right? The output is not really generative, except when you add another layer, which is a diffusion model at the output. So the decoder, text decoder itself does not understand like truly the essence of those other modalities. And I gave an example at the bottom where you have like an image encoder. The second limitation is like right now is like kind of the Wild West of multimodality, where everyone just invents a new novel architecture every single day, and it fragments the software ecosystem. So it hinders mass adoption. For example, Llama CPP is like kind of 1 year behind the implementation of the latest LLMs. There's multimodal LLMs because it's just impossible to keep up, right? There's just too many different vision encoders, diffusion models, and etc. And the last part is like none of them are truly multimodal, like omnimodal. What I mean by that is that they focus on human modalities. And when you say omnimodal, we kind of assume many other modalities like robotics, DNA, like CERN data, right? Machine language, all of those modalities which are not human, for example, robotics and like sensor control data and everything, those are not being taken into account into these models. And after you pre-train, all of these current multimodal models, they cannot extend to this new modality. So they break the pre-train to post-train paradigm. Like in the past, where with GPT-3 or GPT-4, we had this pre-training, like very expensive pre-training that does everything, And then you have the, downstream evaluations or downstream tasks that are very easy to add to the model. But these models, for example, QuenVLM, if you want to add, let's say, robotics, it's impossible. You have to pre-train the model, right, on other data. Yeah, so like very quickly, so how do we break free ourselves from these limitations? Let me show you guys. So before we had this like question mark, but here I would propose something called information modeling. So right now the community is kind of exploring toward these ideas, but nothing is like very set in stone yet. So what I mean by this information modeling is that we transition to a new scaling paradigm, right? So while we work on extracting all of this like knowledge from language models and all of these use cases with multimodality and agents, we can also, on the back end, transition to a new type of scaling, a new type of like the next big paradigm where we train on information itself. So we model the information, the raw information. So I'll just coin this term, like large information models, just because I want to give like a tribute to large language models. So what I mean is that instead of assuming that language is the proxy to intelligence, which like humans, we love to do that, right? We have biases. We invented language, so therefore it must be a precursor to intelligence, but I would argue it's possibly not the case. Like if we model the information itself, like from the universe, it could unlock vast downstream capabilities, right, that we have never thought about. So this is an image from like a recent paper called BGPT, like byte models. So they were just training this LLM on like other modalities, just like raw information. The results were not very good because there's a lot of problems with this currently, but it's a good like step, a good way of thinking, right, a good step forward. I want also to note that here it is a tokenizer-free transformer, right? We're talking about a kind of information model, but it's not the same as what people are trying to do right now with tokenizer-free. We're not trying here to improve on language by removing the tokenizer. We're talking about a new class of models. So if you just want to, let's say, improve language modeling, it's possible that tokenization is the best currently. Like, it's hard to beat because there's like kind of theoretical optimums. But we won't, like here, we're not claiming we're going to beat tokenization, but it'll unlock like new capabilities. So here I have a list of like other data sources. You have, for example, the Steam library, like games, right? It's bigger than 1 petabyte. So like that's very, very big. And if you train the model, let's just abuse the chinchilla, like chinchilla law of scaling. If you train the large information model on the Steam library, it's kind of, it needs to be around in the size of 100 trillion parameters, right? And that's just for this, the Steam library. And I'm really abusing the chinchilla law of scaling because it's not supposed to be used the other way around. But it gives you kind of a rough idea. And if you go even further, you have the NASA data, right, NASA. And they have 100 petabytes of data, of astronomical data. And you have CERN, which have more than 1 exabyte. And YouTube has more than 10 exabytes. And lastly, the one at the bottom is the Earth biosphere, right? The entirety of Earth's DNA data is more than 10 exponent 19 exabytes. So that's like, will we ever run out of data? I'm not sure if we're using this, right? And is all of this data useful? Probably not, right? There's a lot of redundancy, but it gives you an idea of like kind of the scale we're talking about. Yeah, so the case for information modeling here is a meme, but there's something called the bitter lesson, right? Which was proposed by Richard Sutton. And he said that the simpler systems with more compute and data will eventually scale better than like more complicated systems that were more specific, right? So like generalized systems that just scale up indefinitely are usually the winners at the end. And the second case, this is one I really like, is infinite downstream potential. Because here, I'll just like give random examples. I'll probably not list them all, but here there's an example, for example, let's say we want to generate the DNA sequence of a newly invented animal using a drawing. So let's say you just draw an animal on the paper, take a picture, and you ask the large information model, what would be the DNA of this animal, right? How do you create this animal? This information model would be kind of capable if trained correctly. You could also have, for example, act in a multiplier environment by directly working with a network packet. So instead of using all of this like programming and this convoluted stuff to control a agent, why not just let it send and receive network packets, right? You just add it to the networking, and it will just receive the packets and read them and output packets. So that would just allow you to directly use it on any application. You could also directly control robots using digital signals. And that has been attempted right now. There's some papers about this where they try to control a robot using output of an LLM. Yeah. And there's like even more, right? The sky's the limit. Like you have, for example, teach a model how to compress data, and then you can use RL to discover better compression algorithms. Because if the model can successfully compress some kind of data, you can now use RL and try to find like novel ways. And you have like differential rendering, you have native interfaces with computers. Yeah. So let's go now a little bit back to the bottlenecks, right? So here you have like all of this very, very interesting and very capable model, but why hasn't it been done right now? So why is it no one is really like pushing this? There's like many issues. So the first question we should ask is that, is the decoder transformer architecture actually capable to generalize to this new paradigm? So information modeling. And the answer is like very uncertain right now. There's some papers that claim that with chain of thought, LLMs are Turing complete. They can do like NP hard problems or even NP complete problems. But that's like very theoretical. So in practice, me personally or like the community is not sure that transformers can do everything, right? So if you model this on, for example, compressed data, for example, zipped data, so that's using, for example, Huffman algorithms, like could the transformer learn this, like undo this while reading the data right by itself without having access to an external decompressor? So yeah, we're not quite there yet because there's so many problems. The first problem, like the major problem, is the wildly different granularities from these models. Like for example, if this model can do both text and speech, right? Text contains a lot of content information, so you have like a description of the world, and it's very, very dense. But if you have speech, now you have like megabytes of just raw waveforms, right? And that's just a much different order of magnitude compared to text. So how do you train a model that can understand both like this very sparse data, which is speech, and then very dense data, which is text? It's very difficult. And for example, cross-entropy loss is also very inefficient in this case. One solution could be hierarchical attention, where attention attends at different levels inside of the model. So some part of the model attend to very dense data, so text, and others attend to like very global information between, for example, images, video, very long context information. There's also huge context length. So this is kind of like the same problem, but not exactly. Because huge context length is not very a problem for example, RNNs. Those can do huge context. But now the question is, can you do both the long and the short contexts? And that is the hardest problem. So you need some kind of basically efficient attention algorithm. So either like n log n attention. I mean, linear attention could be possible, but that could limit the performance of the model at short context lengths. And also attention, we know it's quadratic, right? So it's like it scales very difficultly. But that's okay if we make it efficient enough at different granularities. So let's say if you had a video input and your attention was 100 times faster on this video, it will be fine, right? It's like you kind of delay the problem, the quadratic problem. So if you divide the context length by 100, you could kind of delay this problem. Image and audio files also go up to like a megabyte, 2 megabytes. So you would require a lot of memory to train. The third problem is slow inference. So now if you model bytes and then you do autoregressive generation, you're doing like you're going through the whole model for every single byte, right? That's very inefficient. So how do you fix that? Probably something like MOEs or some other alternative similar to MOE. So now when you do inference, you don't go through the whole model, like let's say 1 trillion parameters. You don't go through the whole model for every single byte. You go through like a subset of the model every single time. And lastly, you have generation order. This one is very interesting. If you think about it, not every data type or like modality requires you to generate kind of left to the right. Some modalities better, for example, when you do drawings, you want to start with like the head, the face, the body, and then do the background or something like that, right? So it's very inefficient to just assume that everything should be generated from left to right. So there's papers recently that explore any order generation for autoregressive LLMs. So they kind of, you have the input, also the positional encoding of the input, and you also give it the output, the position of the output. So you can do like kind of, you start generating at token 3, token 2, token 6, token 5, right? You can do kind of jumping around. There's also diffusion. Diffusion is also very interesting, where it generates the whole sequence at once, like one step at a time. But the problem with diffusion is it's very difficult to do it with like discrete cases. It's difficult to move tokens around. It's like when you do the sampling, you also like are kind of stuck. Like if you get stuck into a local minimum, it's very hard to get out of it. Yeah. So let's show you guys our latest experiment. So everything I've talked about today was like theoretical, right? So we at Nous are currently trying to make this happen at smarter scales. So the first thing we tried was training a kind of image model. So when I say image model, it's not really the traditional image model. We trained on image files. So we took BMP files, and we trained a model where 1 byte equals 1 token. So we just gave the BMP raw bytes to the model. And the vocab is like 256, right? It's almost non-existent. And you have plus like a few special tokens. And this model was like 600 M. We like tweaked around. We trained like 20 models until it like worked. And this one was the first time that it worked. And the for example, data set was data common pool, which is a varied like common crawl of the internet. It was a 300 gigabyte subset, so the model was trained on 300-bit tokens in quotes, because one token is not the same as text. Here it's probably less informative. So we trained, like this model was trained very little. The image were resized to around 8 kilobytes per image, so it was like 48 pixels wide or height. Pre-trained at 32K context, so 4 images per data sample. And the interesting thing is that we are working currently on a paper called Lighthouse Attention, which is a new type of hierarchical attention that we use for this model. And the paper is going to come out like soonish, but don't count on that. It's very early. But it did work with this model, especially because it was compatible with flash attention too. So we could gain a 4 times like training speed boost compared to full attention. So this training took 1 day on 64 B200s. And let me show you the, I mean, you guys probably want to see the unconditional generation samples. So these are non-cherry-picked. This is the 600 M model, and we trained it on 300 gigabytes of images. And it gave us like this, right? This is very interesting, because these are not images, these are files. So after you generate using this model, you can just dump the bytes into a file and open it with Windows. And you have all of these like very different sizes, different like content, right? The header is also correct. So this model produces like correct bitmap headers. And I think the results speak for themselves. It's pretty cool. It's very similar to the early days of DALL-E, right? Where you had like very blurry images, very small images. Yeah, and this with KV cache inference takes about like few seconds to generate. So without KV cache, it takes probably 1 minute. But with KV cache, like a single image takes a few seconds. We can also do some fun experiments, right? This was only trained on images, but if you can do file completion. So BMP files start with the header at the bottom, like on the top of the file, but the BMP format goes kind of backwards. So it goes from the bottom to the top. So here we gave it on the left the input. We kind of like just truncated this image at the middle, and then we let it complete, right? So it can do completion. So we know the model is working. So this is conditional generation. We can also do stuff like give the header of a wide image. So you start, the prompt is like the start of the BMP file with a wide, the kind of wide format, and then you let it generate the data. And this is what you get. You only get like this exact size of image. And this is also pretty cool. You can see here like some, there's like some, I think, I don't know what those are, but I can see like buildings with people in front. I see like a gym. I see a car here. It's very interesting. And you can also do the reverse, like tall images, right? So with tall images, you can see the distribution is different than wide. Like wide, you mostly see buildings and cars and stuff, but tall, you see like people. It kind of looks like phone images, right? Phone photos. So they are lower quality. So it's very interesting. So what can this model do? This model, the first model we trained, not much, right? It was only pre-trained on image files. But potentially, this can be extended to like image editing, image colorization, upscaling, depth estimation, segmentation, and all of those won't require architecture modifications. You would only need kind of just change your data set and then fine-tune your model, right? So this model was pre-trained, possibly can do this. And this model was only pre-trained like a few days ago, right? So Theo here, shout out to him, he's the one that pre-trained this model. You see it sitting on front. So this is a very early model, we're still playing around with it. And we hope to extend this to many other file types, like audio, text, 3D model files, like entire websites, right? This model could potentially learn how to generate just the entire folder structure of a website, because it's just data. I hope you guys like this presentation. I hope it was interesting. Thanks. And if you guys want to look at the images, there they are. Do we have time for questions?
Yeah. Hi. Thank you very much. Oh, over here.
Okay.
Howdy.
Hi.
Yeah. Yeah. Thank you very much for the presentation. I actually find this very interesting. I've personally been exploring some other architectures outside of transformers as well. One that has come up a lot is like SSMs. So like Mamba, and recently IBM released like a Bomba architecture. So it's kind of a hybrid hybrid attention, as well as kind of the linear inference speed for generation. So I'm curious, like, one of the downsides of doing like character level or like byte level tokenization was always like having sort of semantic representations of different things. So for example, here, like the representation of a building and then being able to like continue the building, or a representation of like a human and then another person right next to them is kind of lost sometimes without having like another form of tokenization. So what are some mitigations that you can think of in either architecturally or in the attention mechanism underlying, or just in general, like as a research problem, like how do we embed these sort of semantic relationships between bytes from one area of the file or to another, or even across files, perhaps?
Yes, I think, me personally, I think that is more of a kind of a data issue, because the model, if expressive enough, can learn kind of these dependencies by itself. So if you look at the previous like decoder-only architectures, the reason why we came from encoder to decoder-only was they assumed that decoder-only could also do like kind of the encoding at the same time, but within the model. So if you're not, you don't need to extract these representations outside for other use cases, and if you only assume that you use these representations within the model, I think it's not necessary specifically to like kind of deal with this issue. So it's like if you scale big enough, the model would be able to kind of have this internal representation of buildings. And here in this image, you can see it did successfully model like an image of a building. So I think it still understands kind of what the building is. It's just like not extractable, right? It's just this model, like if you look at a single byte inside of the model, the representation is like completely smeared between like 5, 6 bytes, right? It's not in a single byte anymore. Does that answer your question? Yeah. Okay.
Hey, so I guess going back to your earlier slides, you were kind of like making this pitch for different types of data and like how bytes would offer like a central way to train models. I guess I was struggling to understand like how something like CERN data or things like that would like provide value, like given, I guess like in language models, we did language because of books and text, but I'm not quite sure how that fits in.
So this
given it's like particle trajectories and
yes.
whatnot.
So, okay, so this is a very hard question to answer, but my intuition on this is that you don't know what the data contains, right? The CERN data contains like ground truths about the universe. And is it useful for the model? I don't know, like how useful this data would be to the model. But given a big enough model, let's say you build a 100 exatrillion, like parameter model, right? That kind of scale. At that point, would the model benefit from having CERN data inside of it? Probably, because if it had access to that, it would be helpful for physics research, right? So my thinking about this is that when you scale up the size, it makes the model can read more information.
Got it. And a quick follow-up: are you certain in the images generated that you're not recreating images from the training set there?
Yes, because we've checked, and also here the conditional is not the same. Like you have variations. This is a ground truth. It's not the same.
I see.
Yeah.
Okay, thank you.
We don't have time.